Over to you, Nikhil.
Great. Greg, you can go ahead.
Okay, do you see my screen?
Yes, perfect.
Hello, I'm Greg Skolmoski, and I'm going to talk about project management. And so this is where you fit. I'm a project manager, and I'll be working with programmers like you. So let's begin. I'm going to make a number of three key points. First of all, where does QISKIT fit? Second is that how does QISKIT fit in the world of project management? And then finally, next steps. Where can we go after this week? A little bit about myself. I started in projects in a hospital in Canada, and my very first project was to install a new computers, and these were the very first ones with a mouse. So no one really knew how to use Windows. So that was my first introduction to a technology project. One of the things was that at that time it was software engineering projects for finance, and I didn't understand it. So I went and did a PhD in project management at the University of Calgary. What an amazing experience! And I found the Project Management Institute chapter, and I volunteered and got to know the people. And one thing led to another that I was invited onto the Project Management Body of Knowledge Update Committee. The PMBOK Guide is the #1 selling project management book in the history of project management. So I'm very fortunate to be one of the authors. I wanted to teach project management, so I went to Abu Dhabi and I was there for 17 years. It was an amazing experience. But I wanted to practice what I professed. So I left academia and returned as a project manager for a new hospital in Abu Dhabi, Cleveland Clinic. And this was a $6 billion hospital. Amazing. They wanted to get the best surgeons and physicians, and we promised them that we would give them world-class technologies for their treatment and research. I delivered 18 major projects during my 8 years. And one of the things that I found out is if you work with IT security long enough, you're going to hear them say, don't build what you can't protect. So what I did was I invited security teams into my planning and design phases. And so we built systems that were easy to protect. And because of this designing in security, I won a major Middle East award from Chief Information Security Officers. Well, I wanted to research and teach again, so I came to Bond University in Australia. And after about 3 years here in 2021, my very last project that I was leading, it won a major innovation award. So we connected pacemakers and defibrillators, connected them with Bluetooth, sent the signal to the cloud in the hospital. We collected data for about a year, and then the surgeons published a journal paper outlining the improvements to health. And that ended up the #3 medical innovation in the world. We had an amazing team, and I found out that this project management really worked. Shortly thereafter, I was asked if I'd wanted to write a book. And so I said, yeah, well, I wrote a book about project management and cybersecurity. I continue to write books, and my last two books were about quantum, and I joined the Tasmanian Quantum Network, and we won an international competition for our strategy based on my book. And last month, in September, I was honored that my 4 books won a major award from the Australian Institute of Project Management, Research Excellence. So I'm going to share with you quantum technologies from a project management perspective and make the case that QISKIT programmers will play a fundamental part in these technologies. So why QISKIT? One reason there's a demand for these transformational technologies. We don't do QISKIT programming for ourselves, we'll do QISKIT programming for others. The World Economic Forum has predicted that quantum will change the world. So find out how quantum will transform society. And this report outlines many business cases for the adoption of technology and its impact on society. So QISKIT programmers will make these changes possible.
John,
This future
Master,
is
on a ladder
only
this thing.
possible with you. Uh, Nikhil, there's some interference. Can someone mute their microphone, please? Thank you. So you have an amazing opportunity ahead of you. My recommendation is to be like a sponge and learn. Leave social media away for a while, focus on the tasks at hand, and indeed, tonight, tomorrow night, review your notes, make the best of it. This is an amazing opportunity for you and for society. I want to share with you this statistic. $35.5 billion is the global investments in technologies in 2022. So it's a little bit of an old statistic, but it's often recited. But for me, it's not the numbers. Rather, it shows how far ahead China is in leading these technologies. So more than 15 times the investment of India and my country, Canada. We're really behind. And in Australia, look at the bottom. So I have a lot of work here in Australia to help catch up. But here is an interesting point. At the beginning of this year, China announced a further 140 billion US dollars investment in quantum and related technologies. So they are investing a lot of money. They want to take the leadership role. But here's the worrying point. Microsoft, in their digital defense report this year, has identified these 4 countries as the leading actors of hacking, state-sponsored hacking. So that's North Korea, Iran, Russia, and China. So not only is China investing and researching in quantum, they're also stealing from researchers in India, United States, Australia. So when we put these two things together, the investment in technology and theft by state-sponsored hackers, it's something to be taken serious. Okay, there's 3 types of quantum technologies that we can use project management as a delivery method. I'm going to talk a little bit more about quantum computing, but I want to briefly touch on quantum sensing and communications. Quantum sensing, it's sensing, but more precision, more accuracy, more sensitivity. So, for example, we'll be able to detect cancers and the markers of the disease 5, 10 years earlier with these new sensors. Quantum communications, that's the new internet, the backbone. And China is leading the world in quantum key distribution with the internet and satellites. And so it'll be a new backbone, a new internet. And this will allow autonomous flying vehicles and it's just going to change society immensely. So this is where China is also leading. Now with quantum computing, this is where QISKIT comes into the computing and its applications. QISKIT is unlikely to be used in quantum sensing and communications, but we will see it in quantum computing. So let's look at that. If you look at the leading countries in the world, they all have quantum strategies. They all want to be the best. They all want to be leaders. But in each of these documents, they outline a major, major constraint. And the constraint or the problem facing all these countries is there's not enough quantum talent. Well, amazing, this opportunity you have this week to upskill and learn. So congratulations for doing this and your dedication. You are filling the gap. Amazing. But let's look at why there's a growing demand. So there's a growing demand for quantum, for innovation, to do new things, but also hackers want the quantum computer because it'll give them the advantage. So there's a growing trend that organizations are adopting quantum technologies to optimize business processes. I want to talk a little bit about the dual potentialities of quantum technologies. Quantum is a technology, and technologies have dual potentialities, meaning they can be used for good purposes and for bad purposes. So I can use my email to threaten a student, or use my email to encourage a student. The technology is neutral, it's how it's used. Same for quantum. So I come from healthcare, and quantum computing will transform healthcare. So these are the positive benefits. But the only way we get these positive benefits in healthcare is to implement quantum technologies through projects. We just can't go to Lulu Center and buy these technologies. We have to plan, implement, and optimize through projects. Now, the hackers want a quantum computer, and we can protect our organizations through projects to strengthen our encryption, our cryptography. So the dual potentialities, the good stuff and the bad stuff, it's all implemented and protected through projects. So why do organizations want quantum? One of the main reasons is they want to optimize flows. So an airport, think about all the different flows through the airport. My luggage, my suitcase, goes through the airport and ends up on the plane. I take a different path. I go through immigration, and I go through security, a different flow. The cabin crew have a different flow. The security that keeps us safe in the airport, they have different flows. People sometimes come on board with their dogs and cats. They have different flows. So we have lots of flows through airports. We want to minimize time, maximize throughput, minimize the carbon footprint flows. Supply chain, we also want to maximize. Manufacturing flows through a manufacturing company like BMW. They want to maximize throughput. University admission flows, clinical pathology flows. So when you were admitted to the university, they admitted you through a flow. So this area of flows is ripe for PhD research and full scholarships. So with further learning, think about master and PhD study. So how do organizations adopt quantum technologies to optimize these flows? How is it done? Well, that's what my books are about. Project management and program management. How to plan, implement, and optimize these technologies. So where do we start? Because quantum is technology, I recommend we use ITIL. ITIL is the Information Technology Infrastructure Library. This is a guide for IT professionals on how to manage technology. So it's how to deliver digital services like email, digital services like online libraries, digital services like supply chain uh, applications. Quantum is a digital service. So how do we begin? Organizations begin with there's some sort of a demand, opportunity for technology. We don't implement technology because we have nothing to do. We implement technology because there's a demand for it or an opportunity. This is like quantum. So according to ITIL, we can follow their practices to guide our projects and operations in IT. So it begins with strategy management practice. This is about 6 to 10 pages, I think, and it explains how to develop an IT strategy. So if we want quantum, organizations should start with updating their strategic plans to add quantum. Once the strategy is updated, then there's funding or approval to proceed, and then it comes to me and you to develop quantum technologies through the project delivery approach. So here we plan and implement the technology, and I use more practices from ITIL. ITIL has a project management practice, risk management practice. For me, especially important was service validation and testing. These are the requirements. So ITIL guides me on how to capture these requirements, validate them, and after it's been built, test the system. It also guides me on how to release the new technology into the business operations. This is where QISKIT fits in. I will be working in the future with programmers like you to create new applications. Then we hand the application over to IT operations, and then they deploy it to the end users. ITIL also has practices for IT operations. For example, it explains how to manage the service desk. And if something goes wrong, my printer doesn't work, I forget my password, there's an incident management practice so that we can look after the end users. So IT operations, they deploy the new technology to the end users, and the end users use quantum to provide value. So the business use cases outlined by the World Economic Forum is an example of the value. Better batteries, improved green energy, ending world hunger, for example. So value then is produced, and eventually they will want continuous improvement. And so ITIL has service requests for new systems and to improve the ones we currently have. So ITIL guides IT professionals from end to end, from strategy through to projects, through to IT operations for these technologies. Amazing. In continual improvement, we might also see requests for additions or to fix things, and QISKIT programming could also occur here. So you can see the skills that you're developing this week are critical, and we have a way to manage them. So learn about ITIL. There's also a competing service management system called COBIT. I come from an ITIL background, but COBIT is almost exactly the same. So whichever you prefer, QISKIT has a place. So where do we begin? ITIL says start with strategy. So what we need to do is have organizations update their business strategy to use quantum technologies, maybe to disrupt the market or to add new services to take market share. So then the different departments will create business cases on how to introduce quantum technologies into manufacturing or how to use quantum technologies into healthcare. And then we will use the quantum technologies outlined in the business cases to achieve corporate strategy. So right now, organizations need to be updating their business strategy, developing business cases, and then implement projects. Well, once the business people have identified their new strategy for quantum, it then comes to us, the technology leadership team, to update the technology strategy to bring quantum technologies into the organization so that quantum business use cases can be implemented. So what we will have is an updated technology strategy that outlines how the organization will have a hybrid environment of classical technologies and quantum. We will still use classical technologies for email. We'll still use classical technologies for access into our library systems. But we'll use quantum technologies for more advanced applications. So we will have both hybrid and classical with quantum. After the technology strategy has been updated for quantum, then it comes to the IT security leadership. Now that we have new technologies, how do we protect them? And so they will look at two major elements. They need to adopt quantum safe technologies. That means new encryption. So this is called post-quantum cryptography. So after the quantum computer, post-quantum cryptography. But here's the problem. These new cryptography has never been tested because we don't have a powerful enough quantum computer today. So there is a risk that we will protect our organization with this new post-quantum cryptography, but it doesn't work. There's vulnerabilities. So then the organization will have to update the cryptography with version 2. Amazing amount of work this will require. And then we will have quantum cyber readiness. So we have quantum business strategy, technology strategy, and cybersecurity strategy. So there's a demand for quantum. We will implement projects for people to upskill them, like learning QISKIT, streamline the processes for a decade of projects, and implement these technologies. And so for me, it's just hardware, software, and integration. And I know how to do this. All IT project managers implement hardware, software, and integration. And so we implement these technologies to generate value. Again, it's just ITIL. Demand, projects, value. Let me show you some use cases from healthcare. This is based on the Kubo algorithm and a quantum annealing computer. This can be done with these early computers. So we want to optimize caregiver scheduling, like the intensive care unit nurse, the doctors and physicians and nurses in the emergency department, in the laboratory, and so forth. So we want to optimize so we have just the right amount of people to look after our patients. We also want to optimize the flow through our laboratory, our pathology lab that does biopsies on tissues, take blood tests, and analyze other types of samples. So what we want to do is optimize the people, the expensive equipment to testing, and all the expensive reagents. We want to optimize the flows through pathology labs. Likewise, we want to optimize the work that comes through the pharmacy. We also want to optimize learning, human resources. As you know, uh, healthcare requires advanced skills like uh, CPR and advanced CPR. These certifications expire after 1 year. So if they expire, we can't schedule the nurse in the ER. So what we want to do is optimize learning and provide training in the 12th month rather than the 6th month. So we want to optimize learning so that we can optimize scheduling. We also want to optimize the supply chain so we never run out, but we have the minimum viable stock on hand. And we want to optimize finance so that the patients pay the minimum amount and insurance pay the amount that they're contracted to pay. So with one quantum computer, we can do all these types of optimization use cases. And so I will rely upon QISKIT programmers to help me develop these systems. Amazing. So right now, we have off-the-shelf systems from Epic to do scheduling, pathology, and pharmacy tasks. And at the back end, we have SAP that does HR, finance, and supply chain. Today, organizations are updating their systems for AI features. So right now, hospitals are adding AI to these systems. And in the future, they will be adding quantum technologies, and these will be based on QISKIT. So there's a natural progression that's ongoing, and you are part of it. Amazing. And it's all ITIL again. We do all of this following ITIL. So get your ITIL certification. It's fairly easy. The book is about 200 pages. Most people say it's a fairly easy certification. So this will last you your professional career. So when you go to a new job, you will have an easier time to fit in because you know the ITIL way. ITIL is used by the top companies in the world. So get your ITIL certification and expect an amazing journey. ITIL. So let's look at projects. You are going to be valuable team members very quickly. So these dual potentialities, to get the good stuff into healthcare, we implement them through projects, and QISKIT programmers will be on my team. But we also have to protect the organization from hackers using a quantum computer. So all of this is project work. So what we can do is follow the project delivery approaches in standards and frameworks. Standards represent best practices. Follow me to reduce risks and improve quality. So ITIL is a framework that identifies best practices for IT professionals. PMI, the Project Management Institute, outlines project practices that are best practices. So with these two, ITIL and PMI, we have best practices for IT projects. The one that QISKIT is likely will be first involved in is the DevOps approach. And it's simply a continuous flow of functionality from the developers to operations. It begins with planning. So in the plan phase, we identify the requirements and what we're going to do. And then it comes to us, QISKIT programmers, who code and build, and then the testing team will test, make sure that there's no defects. So we find and fix defects. and then we release it to the IT operations team. They will then have a deployment strategy to deploy the new software to maybe just one department or maybe to everyone in the organization. And then it will be used by the end users, operate, and then leadership will monitor the effectiveness of this new technology. And then there'll be requests for continuous improvement, and we go back to plan, code, build, test, and release. So it's a continuous flow of new technologies and functionality to end users. And you're right in the middle of it. If you want to learn more, you can find out more from the DevOps Institute. Let me show you how the project delivery approach that I use. It's a little bit different, but you will see that it's pretty much same, but different. So this approach that I use, it's designed to reduce risks and deliver the right amount of quality. So projects begin with a demand. We don't do projects because we have nothing to do. So somewhere there's a demand for new technology like quantum computing, optimization. And so this approach is for off-the-shelf software. And so I worked in Cleveland Clinic, Abu Dhabi with IBM for about 8 years to implement technologies. So we worked together to implement technologies like Oracle, Epic, Siemens, and so forth. So this isn't programming, it's off the shelf. It's already been programmed. So it starts with a demand, there's approval to proceed, there's funding, and then it comes to me. I initiate the project with a project sponsor, develop a one-page charter about what we're doing. Then we move on to the plan phase, where we identify the high-level requirements, develop a budget, schedule, in-scope, out-of-scope, risk management plan, and so forth. It's then endorsed by the subject matter experts and then approved by leadership. Then we go into design. We design in security. We design in the standards. So the pharmacy project, we design in ISO standards for pharmacy. So we bring project management, the pharmacy people bring the design in the business case. I bring project management, the manufacturing team brings the design for the software. Okay? So after the design is approved, we then build or configure. This is not programming. This is much like getting a new phone with drop-down menus where we configure. We configure the time for India Standard Time. We configure the time for maybe Australian Standard Time, and so forth. So it's drop-down menus for configuration. Then we test it, and ITIL guides how to test with application testing, unit testing, regression testing, integration testing, and so forth. So here we find out it works, we get user acceptance, and then we move on to the final phase before we hand over. This is called the transition to production. This is identified in release management from ITIL, and there's about 32 activities we did here. So we have to develop a go live plan to move it from the test environment into the production environment. We do final penetration testing, backup and restore testing, develop our final communications for the end users, provide training, and so forth. So these are the final activities before we go live and deploy these new technologies. So we go live, deploy them, monitor that it's working, and then close out. So there we've delivered a system that's used by the end users, and they generate value. So again, you can see this is just ITIL. We have a demand, we have a project that provides deliverables, those deliverables are used, and they generate value. It's hybrid rather than waterfall project delivery because we can introduce iterations to figure out problems or improve the design. Also, we bring an agile attitude. We're adaptive. We're proactive. We front end load. So this hybrid approach reduces risk and delivers the right amount of quality. It really works when done well. But I wouldn't use this for QISKIT because we're configuring rather than programming. I would use the previous DevOps approach if I was working with you. So there we have it, two different delivery approaches. And you can learn about these approaches from the Project Management Institute, the leading project management organization in the world. And you can get certified from this organization. So there we've seen the dual potentialities, that it can be used for good, and we can use the project delivery approach to implement these technologies. But unfortunately, there's people in the world that want these technologies to do bad things. So let's look at that. So there's a severe risk that due to a cryptographically relevant quantum computer, there is a severe risk that data may be stolen and unlocked. So a severe risk means there's high probability and it'll have a high impact on the organization. That's a severe risk. So high probability means it's going to happen. So there's two parts here to this risk. The first risk is that it can be stolen. The second risk, it can be unlocked with a quantum computer. But we don't have that computer today. So the real risk, it can be stolen today, number one, and unlocked in the future. They call this risk steal now, decrypt later, or harvest now, decrypt later. So there's many organizations that are already compromised and they don't know it. But in the future, hackers will unlock their data. It's been estimated that to unlock or to crack or to hack classical encryption, it takes about 300 trillion years. So our encryption today, RSA 2048, is very strong. It's been protecting us since 1977. And it takes 300 trillion years to break this encryption. But with a quantum computer, it's been estimated a hacker can break in about 8 hours. So think of that, from 300 trillion years to 8 hours. Oh my goodness. So what's at risk? The hacker can get this data: financial statements, tax information, research and development, technical data, military strategy and tactics, computer code. All of this is available to a hacker. So they can break in and steal this information. So what do we have to do? We either have to upgrade the technology, but if the new encryption doesn't fit, we will then have to replace the software and hardware. So we will either have to upgrade, and if it doesn't degrade performance with a new encryption, then we will have to replace if we have performance problems. So the experts are recommending that it will take about 9 years to complete this encryption migrations. So this is not a quick fix. It's a sustained 9-year program of projects to safeguard organizations against a hacker stealing organizational data and personally identifiable information. So we have a major privacy issue coming. So what do we have to do? So we need to address these risks and opportunities. So it starts with a business strategy, an updated IT strategy, and a cybersecurity strategy that is aligned. We have strategic alignment. So that's the first thing we need for successful projects. So what type of projects do we need to do? The very first project is to make sure that our locks, our encryption, is rock solid to protect against the steal now, decrypt later risk. So we have to make sure that our current cybersecurity foundation is solid. Next, we do a cryptographic inventory. So what encryption do we have? What are the dependencies? So there's encryption in hardware, software, firmware. Data is at risk in storage, in use, and in transit. We also have to inform people, make them quantum literate. So raise quantum awareness so we have enthusiasm and desire for this decade of projects. We need to optimize project management and our processes, like approval processes are lean and automated. Change management processes are lean and automated. Our go live is lean and automated, for example. We also want to optimize ITIL, our service management optimization, such as the disposition of legacy technologies. So we dispose of them in an ecologically friendly way. So we optimize our processes for project and service management, automate them. Next, we implement quantum technologies, hardware, software, and integrate it with data. Most organizations will join the quantum revolution by accessing quantum services in the cloud rather than an on-premise quantum computer. Then we implement post-quantum cryptography, our new locks, to safeguard organizational data and personally identifiable data. And we work on cryptographic agility. All the endpoint devices have to be secured and their ports locked. We have to stop buying the old classical technology and make sure procurement buys the new stuff. So we have a program of projects that need to be implemented right away. When we do this, we will deliver value. So you can see this is solid ITIL, and it's designed to reduce risk and deliver the right amount of quality. So as a project manager, how would I set this up? We have a decade of projects. So I align with standards and frameworks because these represent best practices. They are generally accepted and they are applicable to most projects most of the time. Okay, so I apply these standards, but I don't do everything in the book. I tailor and combine these standards together. In fact, a good project manager tries to maximize the amount of work they do not do. Let that sink in. We try to maximize the amount of work we do not do. is our cybersecurity foundation. We want to strengthen this to protect against the cybersecurity performance goals. And simply, it's just best practices like multi-factor authentication. When we do our cryptographic agility projects, there's our service management and project management optimization for the decade of projects. Then we implement quantum technologies. These are likely in the cloud. And then we run our cryptographic migrations to install the new locks from NIST, the National Institute of Standards and Technology out of the United States. So this is how we can implement these technologies. We apply these standards, tailor and combine. And this is what my book is about. It came out in January this year, and it was an Amazon top new release. So the most dreaded question in project management is, when do we have to complete the work? Well, the Australian Signals Director, my government, is recommending Australian organizations to complete this program of work by 2030. So complete the post-quantum cryptographic transition in only 5 years from now. But here's the problem. Many experts are saying this is an 8, 9, 10, 12-year project for many organizations. This organization, the Financial Services Information Systems Advisory Council, a global network, is advising that it takes at least 8 years for banks. This expert, Maren Ivezik, out of Switzerland, is an expert in telecommunication projects, and he has published that he thinks it's over 10 years and 350 million US dollars for a telecommunications company to implement this new hardware and software from NIST. So the result I see is that there's going to be a massive movement from complacency to panic. So we're going to see a number of compressed schedule projects to get this done in a hurry. Much like COVID, everyone jumped online, and it was messy. They introduced vulnerabilities. So for me as a project manager, compressed project schedule approaches are the most risky. Only 1 in 4 projects succeed with these aggressive techniques, compressed schedule projects. So what I've done is I've written a new book coming out in December. And this is called Accelerated Quantum Technologies Change Management. And this is about breaking through the barriers of adoption, developing a quantum strategy based on ITIL, and then evaluate whether or not you have the capacity to do compressed schedule projects. So this is fast tracking or overlapping. This is crashing, adding more resources, and substituting. So what I've done research on construction companies and construction projects who use schedule compression. And I want to tell you about the Leishan Hospital in Wuhan, China, that in 2020, they were overrun, their healthcare system, with sick people. They needed more hospital space, more beds. So what the government did, they initiated a project to build 1,200 bed hospital that we can see here in 12 days. 1,200 beds, 12 days. So what they did, they used schedule compression techniques. First of all, look at all the construction workers. There was to 10,000 people on site. 10,000 people that had to be coordinated. The second thing is that they used substitution. also known as prefabrication in this case. They used two sizes of boxes or rooms. They lifted them on by cranes onto trestles. So these rooms were above the ground, and below these rooms was uh, uh, electrical services, AC, power, and so forth. So they used overlapping, they used um, clashing, 10,000 people, and substitution. So they started this project, 12,000 beds, and a few days later there was a change request that moved from 1,200 beds to 1,600 beds. So then they did a change request, approved it, and now it was a 1,600 bed hospital. 2 days later, there was another change request to make it an 1,800 bed hospital. And so then they did a feasibility analysis, impact analysis, approved the change request, and then updated the project plans and built an 1,800 bed hospital in 12 days using schedule compression techniques. So I studied this. I learned what made them successful and how we can implement this on our quantum technology projects. So this is my new book coming out. It's for late adopters. Okay, so it's going to be an amazing week. You're going to learn a lot about QISKIT. You're going to hear some amazing speakers, hands-on workshops. But what next? What next steps can you take? So in IT, we're in the business of continuous learning. IT changes, so we have to upskill. So first of all, finish your studies, do a master degree, and seriously consider a PhD. I'm recommending an MBA for any technology person so that you can have the technology side, like QISKIT and programming, and you will understand the business side, Master of Business Administration, MBA. Because remember, we don't do technology projects for ourselves. We do technology projects for the business. So if you have an MBA, you will better understand what they're trying to do and make better IT decisions. When I finished my MBA, I said, never again. I've had enough school. But after a few years, I got interested and I wanted to learn again, so I did a PhD. Amazing. And certifications. So continue an academic a journey. Also get short, quick certifications. So whatever core area you are, programming, cybersecurity, information systems engineering, whatever, look for certification in your core area. But first, take ITIL Foundation. Graduate and get this done with. It's a simple, easy to understand foundation, but it gives you the terminology and framework to be successful in your IT career. Because QISKIT and programming, that's project work. So get a project management certification. Project management is not just for project managers. It's for project team members as well, so that you will make better decisions in the project. Let me tell you about my friend Rafa Pagan. He has 26 certifications and degrees. He just enrolled in a PhD program. So he is a continuous learner. He is an amazing guy, and he's a role model for me. He reviewed my second book about training. Thank you, Rafa. I appreciate it. So the next steps is continuous learning. But the second step you should have is network. So continuous learning and regular networking. These are critical for your career. So the people on LinkedIn, engage with them. The people you met here at this Fall Fest, network with them, get their names and numbers. Continue your involvement with these people. I did some earlier research, and to have a sustainable career, you need only two things: continuous learning and networking. You do this, and you will have not only a sustainable career, but an amazing career. With myself, with continuous learning and networking, I started out in Regina, Saskatchewan, Canada, a little city of 250,000 people. That took me all over the world, and you can do the same. So my books are about project management. My first book is Shields Up, and it's how to do technology project management and how to optimize processes. Now let me share a little secret with you. If robotics would have been bigger than cybersecurity, I would have written about robotics. But it was my sense 4 years ago that cybersecurity was going to explode and be super critical for national security. So instead, I wrote about cybersecurity project management. But cybersecurity project management is just technology project management. Initiate, plan, design, build, test, do a transition to production, T2P phase, go live, deliver, close out. So it doesn't matter if that's pharmacy project, a cybersecurity project, or a quantum project. The steps are about the same. My next book I wrote with Chris Walker. He was from IBM, and we trained all our doctors and nurses in our hospital on 42 different IT systems: physicians, phlebotomists, accounts payable, surgery nurses, 558 roles. If people were not trained in these technologies, we couldn't open the hospital. So this project was on the critical path to open the hospital. We opened the hospital on time, and we didn't harm patients. They were well trained and ready to treat. My new book that came out in January is about putting all these projects together into a program of projects. My new book is not a project management book, really. It's a change management book. It's a business technology book. So it's about strategy. It comes before project. So quantum cybersecurity is for early adopters, and accelerated is for late adopters. You can order these now. My new book is available for pre-order, and I saw on Amazon it's $16. So it's quite a bargain. What you might also do is just ask your library to order these books and get an e-version of it. Very affordable that way. I chose this company because they make the books affordable. So that's quantum cybersecurity. That is a program of projects. What I do is invite you to connect with me, connect with each other, and make the most of this week. It's a glorious learning opportunity, and I thank the organizers for inviting me. I'm very honored to be with you and speak with you today. So with that, I hand it back to the moderators, and I'd be very happy to take your questions. Thank you.
Thank you, sir. Thank you so much for the insight. We really love the session. And in today's lecture, we are insightful and enlightening session.
Hello.
Thank you so much for the insightful session, sir. We really loved it. And in today's lecture has given us for sure a clear understanding of the broader quantum strategy driving innovation over the next decade. Where project innovation managers and QISKIT programmers collaborate to deliver practical real world solutions. And your insights on a few algorithms helped us to see how quantum computing models complex physical systems and bridges the gap between theory and application. It was really fascinating to learn about its real time use cases in healthcare, really from initiating from the drug discovery to the medical data optimization, showcasing how quantum technologies can create tangible social impact. And we also gain appreciation for frameworks like ITIL, which for sure ensures that technology projects are aligned with organizational goals and deliver structured management and innovation. This lecture also emphasized the value of dual potential of quantum technologies, which is a very crucial point, bridging scientific research and industrial innovation, and showed how quantum computing can drive progress across multiple domains. And most importantly, it encouraged us to adopt to an agile attitude, being adaptive and proactive at the same time, which is essential for success in complex quantum projects. We also recognized the critical challenges in cybersecurity as quantum technologies have the potential to break traditional encryption algorithms. This underscores the importance of robust risk management and careful handling to ensure the quantum innovation remains secure and trustworthy. And it's very generous of you to share the requirements for a sustainable career. As the beginners and explorers who are really enthusiastic to explore the world of quantum and entrepreneurship mindset together, we believe this will become the base roadmap for a number of enthusiasts for sure. We're really thankful for that too. And the session has really inspired us to explore beyond coding, sir, to think strategically, collaborate effectively, and contribute meaningfully to these growing quantum ecosystems. Thank you, sir, for sharing your valuable time, practical insights, and guidance, and for inspiring us to view quantum technology and computing not just as a subject, but as a vision for the future. And now, my dear participants, ladies and gentlemen, this is the time you can use and utilize very well for any of your questions. Is that okay, sir? Shall we proceed with the question and answer session?
Hello.
I said, oh, them to like when I start here, I like to ask you a question related hospital and the thing you mentioned here is schedule compression technique. And how exactly is related to computing, like what my intention to ask this question is like the schedule compression technique using the overhead beds in Wallace. And we also see that what is in what was in the baby stage and how exactly that is related to schedule compression technique in water community.
Yeah. So here's the problem. It's very simple, is that it takes this long to do all the work, but we're waiting. Time is passing. So then we will be left with a small amount of time to do a large amount of work. And so then they will say overlap activities and phases, add more people, flashing. Yeah, and it's very difficult to succeed with this approach. Yeah. So it all comes down to we have a lot of work and we're waiting, we're complacent. And we're going to go from complacency to panic in a big hurry.
So I want to ask you one more question. What is the ITIL certificate you mentioned that would you please be more precise about that?
A little bit slower was the question.
Like you have mentioned about ITIL certification rights. You please be more precise about that. What is an ITIL? If that means that you have.
Okay. Yeah, so with ITIL, there's like beginner, technical, and managerial certification. Everyone takes the first one called ITIL Foundation. So it gives a high level overview on how to do the basics, beginning with demand, projects, and then deliver value. So ITIL Foundation is the first course. It's the beginner course. It's easy, and that's where you should start. And then if you're a technical person, you can take more technical ITIL certifications, like for architecture, and you can take business certifications from ITIL, such as strategy management. So it's a whole career path with ITIL, but begin with the basics, ITIL Foundation.
Understand.
Well, a pleasant morning, sir. Sir, well, the question I have right now is in order to become a successful project manager in the next decade, as you mentioned, as a student, as a beginner like us who started learning QISKIT right now, what skills, like the technical or non technical skills, do we need to start to learn?
One big thing, one big thing you can do that best project managers do. It's called front end load. Front end load. So when you go to university for a new semester, start reading the week before. Read your topics. Don't delay them for later. So front end load, bring forward work, create opportunity in the future to do something fun or to take more of a risk. So front end load, have your 12-hour days at the beginning of the semester instead of having 12-hour days at the end of the semester. Front end load. The technique that I used in every project, and out of my 18 projects, 17 were successful, except the first one. First one, we learned where the weaknesses were, we updated, and then everything else went well. So for students, in week 0, before you start, read, read, read. 12-hour days are easier at the beginning. You're not stressed, you're relaxed, you're healthy. So that's when you can make the biggest progress in your university careers. The first 2 or 3 weeks, front end load, and carry that habit into real projects when you graduate. It's not that difficult. It's a lot of common sense.
Well, thank you, sir. And another question, it's like to get a small information from you, sir. Like, can you share an example of a quantum technology related things that has successfully moved from a lab, like a research lab, to
Yeah.
the industrial use?
Yeah. Now, so we're just starting. The problem is that our quantum computers are not very stable. Okay, so there's not a lot of really good examples for quantum computing. There are some. My old hospital, Cleveland Clinic in the United States, has a quantum computer from IBM. $600 million project for 10 years. And I think it has one or two chip upgrades. So they are using it to excuse me. My old hospital is using today to detect diseases and to create new medications and drugs. There's in the city in England, Birmingham, they are using quantum sensing to look underground when there's a water break. There's water break, so broken pipe. So they're using quantum sensing to precisely find where the break is. So that reduces the time to fix the broken pipe. That's in Birmingham. Quantum communications is connecting organizations with the new internet, and China is leading the world in that, not a lab. Okay, so what a brilliant question to ask, moving from the lab to commercial. It's just starting, and you're at the front end of all of this.
Okay, sir. Thank you very much, sir.
Hello, sir. Namaste from my side. And this is Tanmay from BCA Data Science. So, today I want to ask what are the major lifestyle changes we can witness after the rise of quantum computing? Like, after the rise of AI, we're seeing ChatGPT in everyone's phone and that is integrated in our life. So, I want to know what kind of the major lifestyle changes we can witness after the rise of quantum computing.
Yeah. So that's a brilliant question. Thank you. And I would direct you to look at the World Economic Forum Sustainable Development Goals. This outlines big use cases. So we can, according to their vision, we might be able to solve the climate crisis. We might be able to end world hunger. So there's many big problems called wicked problems that quantum um, uh, might be able to solve. It might be able to cure cancer. I don't know. But it's the QISKIT programmer working with engineers, scientists, physicians, and your collaboration will solve the biggest problems. Some people think that quantum's impact will be bigger than the internet. Quantum's impact has even been compared to fire, discovery of fire. And look at how important fire is. Yeah, I'm looking into the future. I can't tell the future, but I can only read what the smart people at the World Economic Forum are predicting. Yeah.
Thank you so much, sir. Thank you.
We are truly honored with your presence here with us today, sir. And thank you so much for taking your time, not for sharing your such a valuable insights to all our students, but for also for your patience in kindly taking this time answering all the questions and queries. So, guys, let's wind this session up with a very big round of applause for such a lovable session to Professor Greg. And for everyone, whoever is watching this online, and all the dear participants, please fill out the attendance and feedback form so that we also could know how much you loved this session.
Well, it always does. Look at who I'm working with. How many were in the audit? Uh, yeah, yeah. When I was in Abu Dhabi, I worked with many excellent IT professionals from India, lots from Kerala. So to be invited to come to this event, I was very honored. Thank you. Yeah, yeah, good, good. Me too. So thank you for sending. When will you send me an email of the stats? When? Very good. Perfect. Well, I know you're busy. Thank you. Uh, and contact me if you ever need anything. If you need a letter of reference, I'd be happy to speak on your behalf. Okay, I'll go now. Okay, see you.
Today's first session has been done successfully, and I request all the participants to fill out the Google form which will have been sent to you to mark your attendance as well as to let us know the feedback of this first session. Imagine a university that discovers brilliance in the hearts of rural India, offering world class engineering education at no cost. This is Rajiv Gandhi University of Knowledge Technologies, better known as RGUKT or APIIIT, where dreams from villages turn into realities of innovation. Established in 2008 by the government of Andhra Pradesh, RGUKT was created to nurture top rural talent. Its mission is to bridge the educational gap and empower deserving students through a unique integrated pathway to an engineering degree. Guided by a clear vision, RGUKT strives to be a premier institution of learning and innovation. It aims to provide high quality education in science and technology, foster creativity, knowledge, and innovation, serve industry and society with skilled graduates, cultivate leadership, ethics, and entrepreneurship among students. RGUKT campuses are fully residential, vibrant, and self contained. Students enjoy digital classrooms, advanced laboratories, a vast library, and Wi Fi enabled learning spaces. Beyond academics, the university promotes sports, arts, culture, and well being with hostels, dining halls, medical facilities, and recreation centers, ensuring a balanced student life. RGUKT follows a distinctive 6 years integrated BTech program beginning right after class 10. Students spend 2 years building a strong foundation in core subjects, followed by 4 years of specialized engineering. Admission is through the RGUKT Common Entrance Test, which identifies and nurtures promising rural talent. Today, RGUKT stands as a symbol of hope and excellence, a community of thousands of young minds shaping their future through knowledge, innovation, and service. It's not just a university, but a life changing opportunity, proving that where you come from will never limit how far you go. To learn more and begin your journey with RGUKT, visit www.rgukt.in and be a part of the vision that transforms talent into tomorrow's leaders.
QISKIT is a high-performance software. QISKIT is a high-performance software stack built to help developers and researchers harness the full power of quantum computers at the utility scale and beyond. At its core is the QISKIT SDK, an open-source software development kit for working with quantum computers at the level of extended quantum circuits, operators, and primitives. The QISKIT SDK allows anyone to get optimal performance from real quantum computers using their preferred computing environment. Beyond the SDK, QISKIT also includes a suite of high-performance tools and services, like QISKIT Runtime Service, which enables optimized computations of IBM quantum computers through the cloud, using primitives with managed error mitigation. The QISKIT Transpiler Service, which provides state-of-the-art heuristic and AI-powered methods that boost performance for common quantum circuit optimization tasks. QISKIT Functions, a catalog of IBM and third-party services that make it easy to optimize workloads and leverage QISKIT for industry use cases. Whether you're a quantum software developer, a quantum experimentalist, a computational scientist, or just looking to get started, QISKIT's modular flexible framework lets you work at the abstraction level that best suits your needs. QISKIT is designed for extensibility and customization, so you can extract industry-leading performance and tackle new kinds of problems. A high-performance codebase means the QISKIT SDK works faster, uses less memory, and delivers better results than ever before. And QISKIT also introduces you to a vast community of users and developers who are eager to welcome you and help answer your questions. So what are you waiting for? It's the perfect time to get involved. Get started today at ibm.com/quantum/QISKIT. QISKIT is a high-performance software stack built to help developers and researchers harness the full power of quantum computers at the utility scale and beyond. At its core is the QISKIT SDK, an open-source software development kit for working with quantum computers at the level of extended quantum circuits, operators, and primitives. The QISKIT SDK allows anyone to get optimal performance from real quantum computers using their preferred computing environment. Beyond the SDK, QISKIT also includes a suite of high-performance tools and services, like QISKIT Runtime Service, which enables optimized computations of IBM quantum computers through the cloud, using primitives with managed error mitigation. The QISKIT Transpiler Service, which provides state-of-the-art heuristic and AI-powered methods that boost performance for common quantum circuit optimization tasks. QISKIT Functions, a catalog of IBM and third-party services that make it easy to optimize workloads and leverage QISKIT for industry use cases. Whether you're a quantum software developer, a quantum experimentalist, a computational scientist, or just looking to get started, QISKIT's modular flexible framework lets you work at the abstraction level that best suits your needs. QISKIT is designed for extensibility and customization, so you can extract industry-leading performance and tackle new kinds of problems. A high-performance codebase means the QISKIT SDK works faster, uses less memory, and delivers better results than ever before. And QISKIT also introduces you to a vast community of users and developers who are eager to welcome you and help answer your questions. So what are you waiting for? It's the perfect time to get involved. Get started today at ibm.com/quantum/QISKIT.
So, so, what is QuizKit? KeysKit? QuizKit. QuizKit is an open source software development kit for working with quantum computers at the level of circuits, algorithms, and application modules. This SDK allows anyone to program on real quantum computers from their laptop. In two lines,
Yeah, yeah. Can you hear me? Okay, thanks. Yeah, video, I don't know, video may not work. Can you see me? Let's see. Yeah, I can do one thing. Okay, I can join from my mobile and then sec- yes, yes, the PC, yeah. And the PC camera has an issue. So I'll just join and say hi through my mobile and then turn off the video. That would be better. 1 second. Okay. Yes. Yeah, after a while, I'm going to share my slides. So that time, no need to turn on the video anyway. So I think you can just go ahead. Yeah. Sure. Yeah, I can see, see and hear you clearly. That's not a problem.
చెప్తాం రా ఆయన మీటింగ్ లో జాయిన్ అయినప్పుడు చెప్పకూడదు రా తర్వాత చెప్తాం చెప్పకూడదు రా జాయిన్ అయిపోయిన తర్వాత చెప్పకూడదు విషయం అనౌన్స్ చేద్దాం. హలో.
Yes, I can hear you.
All right, everyone. We had an insightful session on the beginning of day 2, and now let's keep the momentum going. Get ready for more ideas, inspiration, and innovation coming your way. It's time for our next lecture by Dr. Gautam Pal. And Dr. Gautam Pal is the Associate Professor and Head of the Cryptology and Security Research Unit at the Indian Statistical Institute, Kolkata. He's also a visiting professor at the Center for Quantum Engineering, Research and Education, TCG Crest, Kolkata. He obtained his Bachelor of Engineering in Computer Science from IIEST Shibpur, formerly Bengal Engineering and Science University. His Masters of Science in Computer Science from the State University of New York at Albany, USA, and his PhD in cryptography from the Indian Statistical Institute, Kolkata. Before joining ISI, he served as an assistant professor in the Department of Computer Science and Engineering at Jadavpur University from 2006 to 2013. And currently, he leads the ISI's Cryptology and Security Research Unit focusing on classical and quantum cryptography. Dr. Paul received several distinguished honors, including the Alexander von Humboldt Fellowship from Germany in 2012 and the Young Scientist Award from the National Academy of Sciences, India, in 2013. His research spans classical cryptography, quantum computation, and quantum communication. Since 2024, he has been serving as the regional coordinator of the Mathematical Olympiad for the West Bengal region under the National Board of Higher Mathematics, India. To date, Dr. Gautam Paul has supervised 6 postdoctoral fellows, 16 PhD theses, 24 master's theses, and around 100 undergraduate products. He has authored over 130 peer reviewed papers and 2 technical textbooks, and also delivered more than 150 invited technical lectures, along with over 100 motivational talks, including 2 TEDx talks. And now it's really an honor for all of us to have Dr. Gautam Pal over here for the guest lecture. Over to you, sir.
I hope you can hear me. Mm, yeah, so let me share the slides. One second. Can you please see the screen? Yeah. Okay, okay. Fine, fine. Right. So, yeah. Okay, let me share differently because I think this is better. Okay, can you see the diagram? I have shared one diagram on the screen. No, it should be there. Yeah. So can you see what the diagram? There is some mirroring happening. I don't know why. Yeah. And what about the diagram, like written crypto system and all? Okay. Okay. Nice. Nice. Okay. So, so this is about cryptography and what what does it mean in the classical and the quantum world. So that's what I'm going to speak. So this diagram is very important to understand why we needed a transition from the classical to the quantum domain in terms of cryptography. Okay. So broadly, we can classify a crypto system into two categories. One is symmetric or private, the other is asymmetric and public. Under symmetric, so the name tells you the meaning. Symmetric or private means that there will be one secret key shared between the sender and the receiver, and it will be the same. So the same key will be used for encryption and the same key will be used for decryption. On the other hand, the asymmetric or the public key paradigm, there is an encryption key which is made public so that everyone can encrypt, and there is a decryption key which is kept private so that only the recipient can decrypt. So that justifies the names that are there. And under symmetric, we have two other subcategories. One is called block cipher, the other one is called stream cipher. Okay. The block cipher, as the name suggests, divide the message into fixed length blocks. So the block length could be 64-bit, 128-bit, 256-bit, etc. And then it applies the encryption algorithm on each block independently. So it's kind of a iterative process. If you have to encrypt 1 gigabit of file, then it will encrypt the first the block size, maybe 128-bit, the next 128-bit, and so on to repeat the process. On the other hand, stream cipher, if we think, it is nothing but a bit by bit XOR operation of the original plain text and the key stream, the secret key stream. So that means you encrypt bit by bit. In other words, the message is viewed as a stream, a continuous stream of bits, and you encrypt one bit at a time. So that is stream cipher. Now some typical examples which I'm sure many of you have heard of, and you can Google search and find out more about them, is that in the famous block cipher. What is a famous block cipher? One is AES, the Advanced Encryption Standard. So that is the de facto standard of a block cipher that is used commercially across the world in many applications. And it was standardized by NIST, National Institutes of Standards and Technology, in the year 2001. Before that, the standard block cipher was DES, or Data Encryption Standard, which was replaced by Advanced Encryption Standard, or AES, in 2001. Stream cipher. What are some of the famous stream cipher? Well, you have the Snow stream cipher, which was used in 3G networking, 3G wireless crypto. Then you have the E0 stream cipher, which is used in the Bluetooth encryption. Then you have the RC4 stream cipher, which was used earlier in almost all the internet browsers, and now that has been replaced by Chacha or Salsa. Right? So you can guess probably that box ciphers are heavier and the stream ciphers are lighter, because the operation is less. Operations have less complex. So the question may come that if we are happy with stream cipher, see, I'm going to spend a lot of time on this slide because this slide has a lot of story, and all this story actually connects our journey, the journey of the crypto world from the classical to the quantum. So if we have to understand the fundamentals of security in the classical domain and in the quantum domain, and why this shift happened, how this shift happened, and what are the implications, then this hierarchical structure is very important, and it's important to know where does exactly the quantum cryptography fits. So that's why I'm spending so much time before I switch to the quantum cryptography direct. So as I was saying, that if symmetric key cryptography has a lot of applications that I have already mentioned, starting from online transaction to e-commerce to network security to internet browser, then why was the need of asymmetric and public key cryptography? Famous public key cryptography example is RSA. Even if you don't know the algorithm, I'm sure all of you have heard of it, the reverse Shamir Adelman, famous RSA algorithm, and the elliptic curve based cryptography. Right? So those are famous asymmetric and public key algorithms. So the reason symmetric and private key cryptography, along with it we have asymmetric, is symmetric cryptography has a requirement that we have to share the secret key. Now imagine the sender and the receiver, they are sitting in a room and they are tossing a coin, choosing some random string and writing it down, and then going apart in two different parts of the world. So now because they have shared the secret key, they can use the same secret key to encrypt and decrypt. I mean, to convert the message into a random looking ciphertext and to get back the message at the receiver end. And that's the inverse operation. They will use the same secret. Now, what is the problem? This is not practical. Means we cannot always expect that the sender and the receiver will physically meet. They may not physically meet ever, especially in today's world. The sender may be on one side of the Atlantic and the receiver may be on the other side of the Atlantic, and over telephone they decide that okay, from tomorrow we are going to use cryptographic communication. So now the question is, how will they share the key? Because it becomes a circular problem, and egg versus chicken problem, that which one came earlier. Because if they can share the secret key, then they can share the message as well from one end to the other, because the key has to be shared from one end to the other. The message also has to be shared from one end to the other. So why do it in two steps? You share the message directly. So that means this is a big problem, that sender and receiver far apart. They want to use cryptography, but they can't share it. So there this asymmetric key and public key comes handy, which works as follows. Using number theory or different mathematical operations, you can actually create two keys which we call a pair of keys. So one is the encryption key, one is the decryption key, which are different bit strings, but they work as an inverse of one another. Means that the receiver, let's say, whoever wants to be the receiver, can create this pair locally, the encryption key and the decryption key locally, and can float the encryption key in his or her public domain, so that everyone around the world can get hold of the encryption key and encrypt whatever message they want to send to the receiver. However, the receiver will not make the decryption key public. The receiver will keep the decryption key at his or her own disposal, and whenever any encrypted message will be received at his or her end, he or she will decrypt that using the private, secretly kept decryption key. And if we want two-way communication, no problem, because now another person will act as receiver and initiate the communication. So that's the beauty of asymmetric. So what we can do, we can combine an symmetric and asymmetric key together. Right? So typically the asymmetric key and public key cryptography, because it relies on heavy number theoretic operation, it's typically slow. And symmetric and private key crypto operations are much faster, and therefore they are more practically applicable, more commercially applicable. They have more real-time applications. So we make the best use of both. So use the asymmetric or the public key cryptography to share the secret key that will be used for future symmetric or private communication. Okay, this is very important to understand. So for symmetric and private key communication, we need a same key to be present at the sender and the receiver. It means that has to be shared when they are remotely situated. And this key sharing can be performed using one session of asymmetric or public key communication where there is no need of key sharing. Encryption and decryption will be done locally, encryption locally at the sender end, decryption locally at the receiver end. And the very first message that the sender will send to the receiver is the intended secret key bit string for future symmetric or private communication. Okay, so once we understand this, then we can appreciate that in real world, whether you carry a laptop or your Wi-Fi device into a new Wi-Fi zone, or you log in to an e-commerce server for online purchase, Amazon or Flipkart, whatever, or you log into internet banking and perform a transaction on your account, all of these happen with the help of a combination of these symmetric and asymmetric paradigms. So first, asymmetric paradigm to share the secret key, and then the symmetric key paradigm to actually use the real cryptographic communication. So this, in short, what I just described is the whole gamut of physical crypto system summarized in one slide. So asymmetric slower, symmetric faster. Therefore, we need symmetric in practical communication. However, symmetric requires prior key sharing, for which the asymmetric guy comes to help. Right? We could actually perform the entire communication using asymmetric key only. We could discard the symmetric key completely. However, because asymmetric key is super slow, We want to make best use of it. Use it only once to share the key and then switch to symmetric key with shared key so that we can communicate faster. So at this point, any question in the audience or any point that is not clear, please ask question. Anybody in the audience? Hello? Yeah, I need to hear yes, no, something. No. So I assume there is no question. Next, in 1994, when Peter Shor discovered his famous Shor's factoring algorithm, then that was a blow to the asymmetric or the public key world. Because the most famous, the most widely used asymmetric or public key crypto system was RSA, which the security of RSA was dependent on that if you have two numbers, you can multiply them very easily. But if you have a large number, factorization of that large number is hard. So the security of RSA was dependent on the hardness of factoring. And though classically factorization is very hard, in 1994, Peter Shor published the quantum algorithm, which could factorize any number in polynomial time, polynomial in the size of the number. So what does it mean really? It means that now an attacker sitting in the channel, if it has access to the factoring algorithm as a black box as a tool, then the attacker can break the system, find the secret key, and compromise the system. Okay. So that's the implication. Now, the sender and the receiver may not have a quantum computer, but they have to assume that the attacker has quantum resources because the attacker can be powerful, the attacker has a lot of money, the attacker can buy all the resources of the world. So we can model any attacker like this. So the problem is now, if the asymmetric and the public key crypto system is gone, then this symmetric or private key crypto system, what happens to it? Well, it still remains secure in the quantum world. That means we can safely use the block cipher like AES and the stream ciphers like Cha-Cha Salsa that are used nowadays in TLS 1.3, networking protocol, SSH, Telnet, etc. with possibly some adjustment of the key size. So that's fine. But how to share the key? Fine, we'll do symmetric and private key communication safely and securely in presence of a quantum-enabled adversary. But how, in the first place, we will share the secret key? because that is a mandatory requirement. So here comes quantum cryptography. In short, quantum cryptography was started to replace the asymmetric or the public key cryptography as a substitute of the classical algorithm of key sharing. And then it is understood that the sender and the receiver will switch to the symmetric or the private communication. So, quantum cryptography in its preliminary stage is nothing but a replacement of the classical asymmetric or the public key algorithm in terms of the secret key sharing. So, to cut the long story short, what is the goal of such quantum cryptographic scheme? The goal is to use quantum mechanical system, to use quantum physical system to share a classical bit stream. So at the end of the quantum crypto protocol, the sender and the receiver will have shared a common classical key or common classical bit stream that will be used as the secret key for symmetric or private communication. Okay. So I think this part is now understood.
Yes, sir.
Yes. So any question on this part? I will then switch to the quantum. Okay. So let me share the another thing. Yes. So now what I will do, I will switch to the quantum cryptographic algorithm, maybe 84. Okay. Hmm. So can you see the page 29 of my slide here?
It's not visible.
Okay. I think now it will be visible.
It's visible now.
Yes. Yes, yes. Thank you. So what is BB84? So the acronym BB stands for Mened and Rasa. BB84 is a quantum key distribution algorithm that was discovered in 1984 by Bennett and Gassal. So it goes by their name. And it was the first algorithm that came in order to replace the asymmetric key algorithm or the classical asymmetric key algorithm which we use to share secret key. So BB84 became the de facto standard after Shor's algorithm was discovered and after a fear of, getting or classical key sharing algorithm compromised, that these things came, then BB84 became the de facto standard for quantum key distribution. Means sharing a classical bit string using quantum mechanics and then use that bit string as the secret. So the history of BB84 goes as early as 1970, where Stephen Weisner published something called conjugate coding. Okay? That did not have any foolproof discussion on the security. So finally, Bennett and Prasad in the 1984 paper, they came about a scheme which gave security against quantum adverse. Okay. So what is the basic idea? Let's understand. So to transmit 0 and 1 securely, choose some basis plus cross basis. So I guess the audience is introduced to this basis concept, right? In the quantum. Okay, good. So as you can see, that class is the horizontal and the vertical basis polarization. If you think photon polarization as the physical representation of the quantum information, then the horizontal and the vertical polarization vector can be represented as 0 and 1, so that can become one basis. And diagonal polarization, the northeast and the northwest, which are nothing but superposition of this horizontal and vertical polarization, namely 0 plus 1 by root 2 and 0 minus 1 by root 2, so that can be considered another basis. Now, we know that when we want to measure a quantum state, then basically we have to take the inner product of that quantum state. If we are doing projective measurement, then inner product of the quantum state and the particular basis in which we are measuring. And that will give us the probability of the state collapsing into the particular basis state. So it is our measurement result. So using that simple property, BB84 is designed as follows. So 0 can be encoded into either plus basis or cross basis. 1 also can be encoded in either plus basis or cross basis. So once you select a plus basis, we can, with loss of generality, represent 0 by the kit 0 vector, horizontal polarization, you can represent 1 vertical vector or 1 vector. Okay. Similarly, in the cross basis, we can represent 0 as the northeast vector, 0 plus 1 by root 2, and we can represent 1, I mean the classical 1, as the northwest vector, 0 minus 1 by root 2. So, we take any basis, we encode 0 to 1 qubit, encode 1 to another qubit, and if you use only a single basis, then what is the problem? Then anybody can measure in that basis, get the information and reproduce. Because if the sender and the receiver use the single basis, then the attacker, so that basis will be known to everyone. So the attacker will also measure in that basis to get the information perfectly. Okay. So because of that randomization requirement, we need to choose the two bases random. And similarly, Bob also needs to measure in random basis. Now, because Alice is encoding in random basis and Bob is measuring in random basis, so Sometimes their bases will match and sometimes their bases will mismatch. So positions of the bases match will give the key lengths. Fine. So in short, this diagram explains what explains the sketch of BB84 protocol. So we're going to spend some time on this diagram. So in this diagram, from left to right denotes the position of the bits. That means, 0. If you look at the first row, 0 is the first position, 1 is the second position, then 1 the third position, then the fourth position bit is 0, and so on. So left to right are the positions. Okay, and we'll say quantum particles like photon in different polarization in that manner. So there will be photons sent from first 0, 2 photons sent from the next 2 1s, then 1 photon from next 0, another photon from 1, and so on. So 1, 2, 3, 4, 5, 6, 7, 8. So the 8 bits from here, photons we have to send at least in 8 encodings. So that's the understanding. Okay. Now, if we go down from top to bottom, the different rows, then it represents time, okay, or the different steps. That means the first row corresponds to the first step of the algorithm at time t1, second row, step 2 of the algorithm at time t2, third row is the next, and so on. So I will explain time-wise, the chronologically, what is happening. So let us focus on the first row, ignore the rest of the rows. So the first row, we write Alice's bit. So we assume Alice is the sender and Bob is the receiver. So therefore, the sender, meaning Alice, has some randomly chosen bits at her own disposal locally, which she wants to share with Bob. So that means Alice has this bit string 01101001 that may have been generated by coin toss or by some natural process. And now Alice wants to share this with Bob. That is the so that is step 1. So in step 2, what will Alice do? Now Alice will randomly choose a sequence of bases. Okay. So what are the possible bases? We already discussed that we'll use 2 bases instead of 1. That is plus basis and cross basis. And Alice chooses randomly means she will choose a sequence of class and cross random. So she randomly decides, okay, the first 2 bits to encode in class basis, the next one in cross, the next one in class, and cross plus etc. Okay, so this is a random sequence of class and class without looking into the bit stream. Now the third step means that, so when you look at the third row, you have to simultaneously focus on the first and the second row in the same column. So we'll read column wise. So we'll read column wise the third row in context with the the first 2 row. So Alice polarization. So 0 when we encode in class basis, we have already discussed 0 in class basis is encoded as the vertical polarization, and 1 is class basis the horizontal. So 0 in class, we get Alice's polarization as the vertical vector. So now this is the physical encoding of the logical information 0 in the chosen class basis. So you see the upward arrow is nothing but a physically vertical superposition of a photon. Okay. So that's the physical representation. Similarly, 1 in class basis is represented as a horizontal vector denoted by the horizontal arrow in the third row. Then 1 in cross basis is a northwest vector, 0 in class, again vertical, 0 in 1 in cross, again west, and 0 in cross northeast, 0 in northeast, and 1 in plus rightward arrow. So the third row represents the polarization of photons. Then we choose to represent the logical bits in the first row in the Alice's randomly chosen basis of the second. Okay. So in that sequence. Now, what will Bob do? Bob will choose another sequence of bases randomly. So you see plus, cross, 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 plus, cross, plus, plus. You can write whatever you want. And now, after receiving the physical qubits in the third row, Bob will measure them in Bob's basis and get the measurement result. So now let us focus on the third, fourth, fifth row together in this table. So third, fourth, and fifth row together. So third row arrows denote the input vector, and Bob's basis represents the measurement operator as the receiver end, or at the Bob's end, the measurement basis, and the third row represents the measurement result. So let's look at column wise now. Let's focus on third, fourth, fifth row together, but column wise. So the first column, you see a vertical arrow, right? You measure it in class basis, you get a vertical arrow because the dot product, the inner, the vertical vector is 1 with the vertical vector of the plus basis, and inner product is 0 with horizontal vector of the plus basis. So that means with probability 1, we'll get the last state aligned with vertical polarization. So that means we can decode the information effect. Okay. Now, what happens in the second column, if you see that Alice's polarization is horizontal, right? Encoded in class basis. The Bob's basis is cross basis, which does not match with the plus basis. So if we take inner product of Alice's polarization, which is horizontal, with the diagonal vector, we have 50% probability of getting the northeast vector as our collapsed state after measurement, and 50% probability of getting the northwest vector as the final state after our collapse. So that means now randomly, sometimes the Bob can recover the bit that was originally sent, and sometimes Bob cannot, because of this randomness. Uniformly, it is prone to error, right? Because the bases are not matching. And this is purposely done. So I will explain why. After Bob's measurement, you see that they have public discussion. What do they discuss? So Alice and Bob publicly discussed that where their bases had matched and where their bases had not matched. The positions corresponding to where their bases had matched, because they are now announcing their bases publicly, they will discard those positions, and where their bases will match, they will keep those positions because they are guaranteed to match the encoding bits with the decoded bits. So that is guaranteed. So removing the columns, now you can focus on the columns that are remaining. After removing the columns where the basis does not match, means either in the second and in the fourth row, depending on that, we eliminate the particular columns, and the remaining columns contribute to the secret key. So you know the shared secret key at final row we show at 0, 1 and 0, 1. So now there are several questions that you can ask right at this diagram, looking at this diagram, that what gives rise to the security. So the first question, why can't Alice and Bob discuss publicly anytime? Because they have chosen their bases locally. So why the public discussion has to wait until Bob's measurement happens? That is very critical to the security. Because when does Bob's measurement happens? When the photons transmit completely from the quantum channel and go to the receiver. So if the public discussion happens before Bob's measurement, still find quantum channel. So then we'll know when the basis has matched, then data card will measure basis in the corresponding positions to get full information 100%. So this public discussion of which basis they have chosen has to happen after Bob has received all the qubits, and in the quantum channel there are no qubits flying anymore. So that is the logic. Second argument that one can make is that suppose in the quantum channel the qubits are flying, what if Eve creates a copy of the qubits with herself, okay, which measure flying qubit pass to the, so one will not be aware of the fact that the attacker has made a copy of the state. So here comes another very important principle in the quantum information that's called no cloning theory. It was described by Uters and Zurich in 1980. The famous no cloning theory states that you cannot create a copy of any arbitrary unknown state. Of course, if you know the quantum state, you can create a copy as many times as you want. If you know a state is 0, you can create a copy. If you know a state is 1 or 0 plus 1 by root 2, no problem, you create copies as much as you want. But if your state is unknown, then you cannot create copy with 100% success. So that result is no cloning theorem, and that helps us. And that tells us why any attacker cannot actually have additional photons at the attacker's disposal and create copies of the flying photons to the attacker's photon, so that the measurement can be done later. Cannot do it. It has to let the flying qubits go without copying. It can maximum it can do is to try to do some measurement and resend. So that is called the famous measure and resend data. The problem of that is because attacker will be measuring without knowing the basis, because the box measurement has not yet happened, public discussion has not yet happened. So if the attacker has to attack the qubits, that has to happen after the third row in this table. So between the third row and the fourth, when the photons are flying in the quantum channel. And that tells us that attacker will not have any advantage. So this is in crux what happens in the quantum domain, in the quantum security. So the next, an obvious question is that is quantum cryptography the only applications of is quantum key distribution the only application of quantum cryptography? The answer is not. There are variants of QKD, as well as there are variants of non-quantum key distribution, quantum crypto as well. So there are quantum secret sharing, which is analogous to classical secret sharing. So what I discussed is basically the main pillar of quantum cryptography, which is quantum key distribution, which is used to replace the classical asymmetric key-based communication, so that you can perform the symmetric communication safely and securely even in presence of quantum attacker. But there are other applications such as quantum secret sharing, quantum multi-party computation, which is similar to classical multi-party computation, quantum private query, which is related to client-server based communication, where the client does not know additional information from the server than whatever was the query, and server does not know on which data the client has queried. Then position-based quantum cryptography, that means certain quantum states can be revealed only when the person who is performing the measurement is located at particular physical locations. Okay. So, post-quantum cryptography, is the current buzzword. Everyone is thinking about it. it means is that just because RSA and elliptic curve cryptography is shattered, the question is the quantum key distribution is the only way to replace it? There are other classical schemes which are attacked by Shor's algorithm or the variants of Shor's algorithm that survive quantum attacks so far, which we can use. So there comes the post-quantum crypto protocols. They are purely classical algorithms implemented in purely classical machines, and yet they have the property that they can resist any sort of quantum adversary or quantum attacker so far as our current understanding goes. And not even Schur's factoring, but any quantum algorithm you can think of, Simon's algorithm, Schur's algorithm, any algorithm, they are not fully. So these are classical algorithms that attack the sender and the receiver can use safely to communicate even in presence of a quantum attacker using ordinary classical machines, ordinary classical channel. So that's the goal of post-quantum cryptography, and we know that National Institutes of Standards and Technology had launched a competition to select PQC standardization standard algorithms from 2016 to 2022. It's a pretty long competition. And finally, they have selected 4 candidates so far as the finalist of post-quantum candidate. So, lots of independent interest. So with that, I will stop and take any questions that you may have. So any question? If speaking is a problem, then you can take questions.
Sir, could you please explain about quantum mechanical system to use quantum physical system?
Nandu, what is your question?
When you are
Okay, okay. I understand what you mean. So you see that whenever we have to represent information, right, you need some physical representation. So in the classical domain, when we have to represent 0 and 1, we either choose high voltage versus low voltage to represent 1 and 0, or high current versus low current, or a capacitor highly charged versus discharged. Right. So in the quantum domain, we need quantum particle and their quantum state to represent our classical information 0 and 1. So we can either use photon and their horizontal and vertical polarization to represent 0 and 1, or we can use electron, their spin to represent 0 and 1. So for example, plus half and minus half, 2 spins can represent 2 property. We can use angular momentum kind of degree of freedom to represent quantum state. We can represent atoms and molecules, and atoms in ground state to be 0 and atoms in excited state to be 1. So physically we can represent multiple quantum subjects as potential candidates for the representation of the information zeros and ones. The advantage is that in quantum, because we have superposition of state, because we can have any combination of horizontal and vertical polarization. Therefore, we can represent superposition of zeros and ones. I mean, combinations of multiple states together. So that's an advantage. But physically, there are many ways in which you can encode quantum. Any other question?
Questions? Guys, anyone have any questions?
Guys, if any one of you are having any questions, you can come forward and ask that.
Sir, could you please explain about PQC with examples?
Okay. So let us. Okay. Let me share something to internet.
What I'm asking means you said lattice based, multivariate, hash based. We don't know what are they. What are those? Could you please explain about them?
Yeah. So you can see here, I'm sharing the screen. Can you see that?
Yes, sir.
Yes. As I was telling that this NIST competition has ended in 2022, and they have announced few candidates as the current PQC standards. So they have recommended, okay, this candidate for encryption, this candidate for key exchange, this candidate for signature, etc. So without going into the details, if we want to understand what they are dependent on. So for example, if you look at this table, for lattice-based post-quantum cryptography, we have Crystal, Kyber, NTRU, and Saber as the candidate, right? So, what does it mean by lattice-based crypto system? So lattices are nothing but vectors with integer linear combinations, and in that vector space, what we ask is that what are the hard problems that gives rise to security? So one problem, for example, is the closest vector problem, meaning in that vector space of lattice, if you are given one coordinate point, finding the closest lattice point to that is a problem, because lattices have integer coordinates, right? So they are not integer coordinates, but integer uh, combinations of the basis vectors. So basically, they are integral multiples of the basis vectors. So that means they are like grid points. You can have either horizontal grids or slanted grids, but the lattice points are sitting on the corners of any grid type structure. So you have a grid point. What is the closest grid point? Mathematically, that point, finding that is very, and the security of lattice-based crypto system is based on that property. That means if an attacker has to decrypt the crypto system without the secret key, then the attacker has to solve this particular hard. So the crypto systems, depending on this hardness, is called lattice-based crypto systems. And there are some examples here given on the screen, which individually you can go and study exactly what are the functions they are using, mathematical functions they are using. Similarly, code-based crypto systems, right? So we know that the purpose of coding theory is to provide error resilience or noise resilience. That means whenever you send any signal, this is irrespective of classical or quantum. Whenever you send a classical signal or a quantum signal in a communication channel, it's bound to be subject to noise, and therefore some information will be distorted. So at the receiver end, you try to decode it and get rid of the noise or get rid of the errors. How do you do it? By using the theory of error correcting codes. That's a traditional topic in classical information theory. We can use Shannon code, Hamming code, CRC code. There are many different codes. Even in quantum domain, we can use CSS code, short code, many coding schemes to add redundant bits, redundant qubits, so that we can detect the noise and correct the noise at the receiver end. Now, there is no cryptography in this coding and decoding error removal process, right? The theory of error correcting codes is completely different from the subject of cryptography. But the code-based cryptography is based on the paradigm that decoding is a very hard problem. Unless the attacker has access to suitable decoding parameters, only the receiver can do the decoding, not the attacker. Here, decoding means the decoding the theory of error correcting codes. Decoding, like decoding of Hamming code, or decoding of, let's say, MacLeese code that is given. Because decoding is a hard problem. So we can do a system based on the hardness of coding theory. Encryption will be nothing but adding the noise, and decryption will be nothing but removing the noise. So your encoding becomes encryption and your decoding becomes decryption. Right? So that is the idea behind code-based cryptography. So these are some of the examples that I can think of.
Thank you, sir. But before RSA encryption is solvable by using Schwartz algorithm. It can factorize large numbers like that.
Right.
Lattice can be solved by if quantum computer can solve those lattice points, then it also breaks, sir.
No, so right now, so far, just like we do not see any attack on the cipher and stream cipher in the classical domain, similarly, we do not have any attack on these lattice code-based multivariate crypto systems in the quantum domain, and therefore they are post-quantum crypto, means they are quantum secure. In future, there may be an attack. That's a different thing. So far, in none of the quantum attack models, these systems are vulnerable.
If any algorithm breaks those, then they can also break, sir.
Yeah, they can also break, but then it's have a huge implication. For example, if you can break code-based crypto system in polynomial time by solving the decoding problem, and because coding-based crypto, decoding is NP-complete problem. So basically, then in the quantum domain, you will collapse the P versus NP hierarchy. So which the theorists believe that is unlikely to happen. Right? It's not yet known whether P is equal to NP in quantum domain. We believe that it is not. So it's a very hard complexity theoretic, issues, and they will come up.
Thank you, sir.
Yes. Thank you.
Thank you, sir. This is such an edifying lecture, fully packed with knowledge and learning. It's a feast having to attend your lecture, actually. And on behalf of all the participants and the team, I sincerely thank you, sir, for such an enlightening and highly engaging session on the topic you have covered. Today's lecture also guided us through the fundamentals of classical cryptography, including symmetric and asymmetric systems and their real world applications in online security, e commerce, and even data protection. Your intuitive explanation, analogies, and structured approach made even complex concepts highly accessible, sir. That's really so generous of you. And we also explored the realm of quantum cryptography, where you introduced us to BB84 and the quantum key distribution, showing us how quantum principles replace classical systems and communication. The session beautifully bridged the theory and practical applications, highlighting the evolution from classical to quantum crypto systems. This lecture not only deepened our understanding of cryptography but also inspired us to think about how quantum technologies will transform the data security and the future of secure communication. Thank you, sir, for your time, guidance, and for making such a complex topic both understandable and captivating for all the participants. We really loved this session, sir. And we can wind up this
Thank
session
you.
with a very big round of applause for all his efforts, time, and insights. Thank you, sir.
Thanks a lot.
And to all the participants online and offline, whoever are attending the session, please fill out the Google form which is available in the Google Classroom. The link will be available in your Google Classroom created. Please fill out the form to confirm your attendance as well as to give the feedback of both of these sessions. I hope you have enjoyed and learned something from both these sessions. And the afternoon session schedule is as announced as the beginning. It will go as announced. There are no changes, and please fill out the Google form and you can take a break then. Thank you for attending these sessions very patiently. So there is one more announcement. For the afternoon session workshop, the guest is already here. He'll be taking the workshop session on a digital board. He'll be explaining even all the complex mathematical concepts. So it would be very nice if you could carry a book and pen with you and for the afternoon session. Even if you are
QISKIT is a high-performance software stack.
Yeah, we'll be providing with the requirements like a book and pen, so no worries to you. But have your lunch and get back to the workshop session with all the energy. Thank you, guys.
Kit for working with quantum computers at the level of extended quantum circuits, operators, and primitives. The QISKIT SDK allows anyone to get optimal performance from real quantum computers using their preferred computing environment. Beyond the SDK, QISKIT also includes a suite